Hey, good morning, everyone. Good evening, everyone. Good afternoon, depending on where you are. I am Maria Arcivala. I'm the marketing coordinator at OTOMETRICS, and welcome to our webinar on frequency compression and lowering, new guidelines for verification. Those of you who attended our webinars before know it's generally Mariana, my colleague, who does these, but she's a bit delayed at the moment, so I'm filling in for her for the first few minutes. We hope you're all doing great, and let's start with some of the rules for today. Today's speaker is Wendy Switalski. She's the Senior Market Development Manager in the fitting area for OTOMETRICS. And I look forward to handing over the mic to her in a few minutes. The rules, well, we call them tips and tricks, are as follows. Everybody is muted by default, just to reduce all the background noise. If you have any questions, please use the question bar. You can see it on the right-hand side. And we will try and answer all the questions at the end of the webinar. But in case there are some we can't answer, we will get back to you on an email. And if you are experiencing any technical problems, please feel free to contact my colleague Mariana. She's going to be joining us soon. So Wendy, if you're ready, should we get started? Maybe you can start with a short introduction of yourself, and then we take it from there. All right.
That sounds good. Thank you, Maria.
Yeah, you're welcome. I'm passing the screen on to you.
Okay. So just an introduction. I am Wendy Switalski. I work with the product management team for fitting. I am based in the U.S. in Detroit, so it's morning here. And I'm excited to talk to you about this topic today. Just as a kickoff, just to look at why frequency lowering requires some sort of special verification process, well, we need to ensure, like with all verification, that we're meeting our goal for using it. There are many goals for using frequency lowering. I mean, usually the primary one is to improve audibility, to give access to high-frequency speech cues and enhance speech production in children, but also such things as sound quality enhancement or sometimes even feedback control when there are limitations in managing feedback other ways can be important. And even some reduced listening effort has been reported by users. So the benefits are many, but the potential outcomes of not verifying are pretty significant when we compare it to other, are potentially pretty significant when we compare it to other advanced features. One, we don't know exactly without verifying it if we've optimized it, but two, if we go too far with something like frequency lowering, we could introduce distortion or sound quality issues that could really impact a hearing aid user's performance. So the consequences can be beyond just not being able to optimize the feature, but could also lead into problems with audibility or hearing in general. We, in the past, often recommended using live speech S or SH production as a tool to verify or check your setting, but it's not optimal to do that. Just like using live speech for verification can be challenging, we know there's a great amount of variability between clinicians and even variability between productions. So fine-tuning using objective or subjective measures with live speech produced S and SH is not optimal. So that's why we're going to talk about another technique today. Just as a general high-level overview, in terms of types of frequency lowering, there are still three main types, although there's a lot of blending of these different techniques now with some of the newer versions of frequency lowering available in hearing aids. The first one is frequency compression, specifically nonlinear frequency compression. We're going to take a look at that today, but that just involves compressing the high-frequency signal, reducing the bandwidth, and lowering it in frequency. Frequency transposition is another method that's often used, and that involves cutting part of the signal and then pasting it to a lower area, but not compressing it, maintaining the traditional bandwidth. And spectral envelope warping is similar to frequency transposition, but it also preserves the original signal as well as places it in a lower frequency zone. So frequency compression would be like Phonak Sound Recover 2. Frequency transposition is seen with Widex's audibility extender, or their enhanced audibility extender. And spectral envelope warping is commonly seen with products like Starkey's Spectral IQ. There are a lot of differences in the adaptive nature of these between manufacturers. So it's important to know what the system that you're working with does and how it works. And then the results will look different because of that for each of these different methods, but verification techniques can be used for all. I think it is important to experiment with your devices to gain understanding of the impacts of varied settings, especially when you're implementing a new technique like the one we're talking about today. So what do we need to verify it? Well, we are focusing today on verification with a probe microphone system, and specifically we're going to be using prescriptive targets, the ISTS stimulus, which is the International Speech Test Signal, a multi-language babble made up of female voices. And specifically, we need access to the S and the SH narrowband stimuli that have been extracted from the ISTS signal developed by Western Ontario, Western University, formerly or commonly known as the University of Western Ontario. Those are newer stimuli that are available on Oracle and other real-ear systems that allow you to use this technique. We can use this verification process both on ear with probe microphone measurements and also in coupler measurements completed with Oracle HIT. So you can use it in both ways. It's important, I think, to point out that the first step is always a good foundation. Prior to doing any verification of frequency lowering, it's just necessary that we verify the overall fitting. We have to know the true high frequency input that's being delivered to the patient. And we can't do that in any other way, really, without measuring with a real-ear system. Without knowing exactly how much high frequency sound is being delivered, it's really difficult to optimize. It's impossible, actually, to optimize the frequency lowering settings, and so our outcomes can be at risk. That doesn't mean you can't set frequency lowering, but you can't really optimize it without knowing exactly how much sound is being delivered. We also want to start with a validated prescriptive target or fitting rationale as our first stage of verification. We want to know if we can meet the targets. If we can't meet the targets as a precursor to adding frequency lowering, we really need to think about, should we consider an alteration in the device or possibly the coupling? Do we need more power? Do we need a different receiver? Do we need a custom mold, etc.? Once that step is complete, we can also use that verification foundation to assess the need for frequency lowering by checking the audibility of the S input signal without any frequency lowering. If we can gain audibility without lowering it, then the need for lowering is obviously questionable or reduced unless you're using it for sound quality, which is another potential benefit of frequency lowering. There are other factors, of course, to consider for candidacy, so I just wanted to point out as a starting point, the audibility question is a really good starting point. Do they need it? Can we achieve S audibility in another way? Let's take a look at an example. What you see here is an SPLogram measured in OtoSuite using Oracle. You have the patient's SPL thresholds here and their UCL measured or estimated up here. And then we have DSL targets for 55 dB, 65 dB, 75 dB, and an MPO sweep. These targets were for the ISTS signal. The targets are the dotted line, by the way, and the solid line is the LTAS, the long-term average speech spectrum. So in this specific instance, this fitting as a foundation was a really solid fitting. We were able to match target through 4,000 Hertz within about 5 dB, and through most of the frequency range within about 3 dB. Over on the right, what you see is actually the on-target view available in Oracle, which just makes it very easy to see how close you are to target. It graphs the difference between the target and the measurement curve of the hearing aid, the response curve. So when the lines, as they are right at 0, it means that we met our target with very little variation. So once we have that foundation fitting, we're going to add step 2, which is analyzing the S audibility. What we're going to do is map what's called the maximum audible output frequency. So what you see here is a 65 dB LTAS and a 65 dB target and the patient's SPL thresholds. To map the maximum, I think I said minimal, sorry, the maximum audible output frequency, or the MAOF, the first boundary that we're going to set is the lower limit, and that's right here. That is found, the boundary for that is found at the point where the hearing aid response, the solid line, crosses the patient's audiometric threshold. Where does the LTAS stop being audible? And that's right here, just before about 3000 hertz. Then we're going to plot the upper boundary of the MAOF. That's going to come in where the percentile, or the envelope, crosses the patient's thresholds. So right about here. So the range in between the LTAS threshold intersection and the upper percentile, or envelope, and threshold intersection is the MAOF. This is going to be our new kind of target zone for placing our S stimulus. Once we have that mapped, or at least in view, and we know where that is, now that that becomes our target, we can actually present the S, narrowband S, stimulus without any frequency lowering. We do this just to analyze the S audibility. In this case right here, that's what I've done with this blue curve. This is the narrowband S. Now, the narrowband S has a peak, and it also has an upper and lower shoulder. So what I want to do is I want to make sure that the S peak and upper shoulder moves into this MAOF zone. In this case, looking at this, without adding any frequency lowering, one, we don't have any S audibility because it's not crossing the patient's threshold. And two, it's certainly, along with the peak and upper shoulder, is not even close to the MAOF zone. So in this case, if we were looking at this, this would be a strong, good case for adding frequency lowering. So that's what we've done here. It's important to start adding frequency lowering a click at a time, making gradual changes. And I always start with the default. I think the default is a great place to start. So what we've done is at the default setting, we've repeated that S stimulus, and you see that in teal right here. So one, I can see that I have now made the S audible. The peaks of the S are just crossing the patient's audiometric thresholds into their dynamic range, but I certainly haven't moved it into the MAOF and the shoulder for the peak or the shoulder. So in this case, I would slowly start adjusting the frequency lowering strength. And by adding, in this case, 1 to 2 clicks, the S now falls within that MAOF. It's audible, it's above the patient's threshold, and the peak and the upper shoulder fall within the MAOF. And that's as far as we need to take it. It's recommended that we be as conservative as we can. I'll cap that at the end with a little bit of evidence about that. Next, to make sure that we've really optimized this setting, we can add another stimuli, which is the SH narrowband, the narrowband SH stimuli, which has also been extracted from the ISTS. The goal is to separate the peak, seen here in orange, and the shoulders from the S peak and shoulders. Now in this example, this is one where a trade-off was required between giving S audibility and SH separation. This is a common kind of dilemma that we face, and it's important to use clinical judgment as always to decide, should we back off on the S audibility, or have we gone too far with the S audibility? But usually if you have made the S just audible, you're not going to be able to adjust the SH much beyond that. Some hearing aids will give you flexibility to do that, but certainly use your clinical judgment and accompany this in adult patients with their subjective input, or with caregiver or maybe a therapist input in pediatric patients. Just to touch on how we would set this up if you have an Oracle system, We do these measurements in the Aided Response tab. And within the Aided Response tab, over here on the right, you see a setup that I have a protocol that I've built for frequency lowering. And what I've done is started with the ISTS at 65 dB, because I always want to reference my baseline fitting. And then I've added various buttons or options for the S with frequency lowering off, for the frequency lowering at default, and the frequency lowering at the final optimized setting. Additionally, I've added an SH presentation. This is how I like to look at it, just to see where did I start, where was it with no frequency lowering, where did I start with frequency lowering, and there was my final ending point, and how does the SH stack up as well. If you need to set this up on your system, you just use this drop down shown over here on the left, the little purple arrow, for example, and this is where you can access your signal types and your levels. You want to present the narrowband noise S and SH at 65 dB. If you look on your system and you don't see these options of narrowband NBNS and NBNSH, then a software upgrade would allow you to have these. So just contact your OTOMETRICS team. Additionally, for optimal view, we need to be able to look at the percentile or the envelope of the aided hearing aid response. So in the overlays section for OtoSuite, you'll find a button to turn that on. It's called percentile. So let's take a look at a case example. I have two case examples to show you. The first one is frequency compression, like we looked at earlier. This is the baseline fitting, and I just wanted to point out that it was quite a good fitting. We are only at 4 dB. Are we more at 4,000 hertz? Are we more than 5 dB off? We're about 10 dB low in gain. So we would want to make a decision about whether or not we want to get closer with a more powerful hearing aid, or if this was the hearing aid that we needed to use for whatever reason. What I've done in this video is shown you the process. After I've done my baseline fitting, I use my protocol for frequency lowering, and I achieve just a recheck of my 65 dB ISTS hearing aid response. That's what you see right here. Next, with frequency lowering turned off, I present the S stimuli, and that's what you see right here. Now my MAOF starts right here at probably about 3,800 hertz, and it's quite wide in this case. It ends where the peaks cross the threshold at around 7,000 hertz. So my S, while it's audible, the peak is over the patient's, it's not in the MAOF zone. So in this case, I turned frequency lowering on, and I presented the default setting. And you'll see that right here. Now I've achieved my goal. It actually has moved into the MAOF. But when I took a look at this, what I saw is that we might be able to achieve that same goal with a less sensitive strength of frequency compression. So I actually went back into the software and I chose a less sensitive, a less aggressive setting than the default. And that's what you see right here. Now by doing that, I was able to use less frequency lowering, but still maintain my goal because my peak and my upper shoulder are well within this range. So in this case, I actually turned frequency lowering just less of it to meet my goal. And I would not have known to do that without using this process. And then with my final step, I present my SH. And what you'll see is that I was able to achieve peak separation. Here's my peak for SH and here's my peak for S. And definitely upper shoulder separation. I'm sorry, lower shoulder separation, although my upper shoulder is overlapped. To look at another example, we can look at frequency transposition. Now this one will maintain the original bandwidth of the signal, but it will move it. And frequency transposition as a whole generally moves things lower than frequency compression. You'll see that. So here was my baseline fitting, again, a solid fitting. And then I'm going to show you the same process, just a different method of frequency lowering. Here's my baseline fitting. And after that, I will activate my S in isolation with no frequency lowering turned on. And in this case, not only am I not in that MAOF zone, which is right here, I'm not quite audible. My peak is in the MAOF, but I'm not quite audible. So I activated frequency transposition. And what you'll see is that this specific setup actually maintained some of the higher frequency signal, the S, and then also reproduced it down here. So whenever you see two peaks, when you see the original peak and a lower peak, it's the lower peak that you want to fine tune. So when I look at this lower peak, because this is a transposition, it's moving it much lower. So I'm not just looking at the MAOF. I'm actually now down into the lower range of the MAOF. I can see that I do have audibility, but if I want to give a little bit of a stronger setting for stronger audibility, I have two choices. In this case, I compared by making the frequency lowering a little bit stronger, frequency transposition a little bit stronger. You'll see that here. This was the next step, so it was a pretty big jump. But in this specific hearing aid, I also have the opportunity to leave the S sound alone, to leave the transposed sound alone, but increase the gain, and that would be another option as well. However, if I did want to leave it at this setting, then I can also check the SH. And even with that stronger frequency lowering, I can see that I've definitely kept my peak separate. My peak is here and my peak is here. And kept my lower shoulder separate. Just to look at a comparison side, both have lowered frequency, both have, we presume, improved audibility of S and SH, but they have very different outcomes. Very different appearances in the verification screen. This is our final S and SH for our frequency lowered compressed stimulus. You'll see it's very narrow compared to the original stimulus. And this is our transposed stimulus, much broader and moves things to a lower point. Just to look at a review of the evidence, in 2016, Scoli et al. Evaluated this technique in 2 studies, and they had some interesting findings. I do have some references and resources at the end to share with you. One was that the first finding was that the ISTS extracted S and SH, like we've shown the use of here, they closely resembled the shape of the original S and SH in running speech, and they were 4 dB of the presence of the fricatives, as they would be in running speech. And that's actually important because what they found is that some instruments demonstrate a preference or a stronger aided response for fricatives in running speech than for those in isolation, as was produced with fling recordings. That's important. We want the hearing aids to be able to give a differentiation between the S sounds that would occur in running speech and maybe some sort of environmental ambient noise that was similar to an S, a constant sound, or but not a fricative in speech. So the fact that the hearing aids have that differentiation is a pretty smart aspect. And being able to use a stimulus that will trigger that stronger aided response is important. They also found that listeners that reported the audibility of S and had maximized differentiation of S and SH tended to have the highest performance. Now, this specific subset was done on adults, but there are many other studies on various frequency lowering techniques that you can analyze and review. But that indicates that, one, we do have to provide verified audibility of the S and maintain the greatest level of S and SH can in order to aid performance and meet our goals. That's what we have today, and we can take questions. I wanted to point out these references and resources, and if you would like the handouts, just let us know. We will actually email these out to those of you that are attending so that you can actually take a look at these resources for yourself and reference them after the talk. One other resource is definitely your hearing instrument manufacturers. they can provide you with very detailed frequency lowering information and fitting recommendations for their specific hearing aids, and also give you an understanding of what the various adaptive features are within the hearing aid, because that makes a difference as well. With that, I'm going to hand back over. I'll pause a moment.
Hi, Mariana has actually joined us now, so she's here.
Okay,
Everybody,
great.
I hope you enjoyed the webinar as much as I did. Is there any question from the audience? You can type it in on the right side of the screen. You can type it in any questions. Wendy, is there any difference between verifying frequency lowering and frequency compression? Is there a different recommendation either than you look at the second shoulder or the third shoulder on the S, right?
You look at, yeah, you look at the peak and the upper shoulder.
Yeah.
And it's actually not always clean cut. You sometimes have to make, there are times when you may not be able to achieve peak and upper shoulder audibility. And at that point, you just go with the strongest level you can, where the patient still reports good sound quality. So this is, I would think of this technique as the starting point, but there are a lot of accommodations that have to be made for each individual fitting. But it's the peak and the upper shoulder.
I was thinking about the transposition and the compression, if there's any different on the protocol.
Any different, what, Mariana?
On the protocol?
Difference in the protocol.
Yes.
There's a difference in the appearance of how they look, and there are some differences, as we kind of showed in the slides, that transposition moves beyond usually the MAOF. So you want to stick with audibility and as close to the MAOF as you can get, and not going any further than you need to. This is a feature that most recommendations are to use it conservatively.
Okay.
It's best in small doses. We'll say that. It's best in small doses.
Yes. Do you have any experience on the different manufacturers? Is there any manufacturer that is more aggressive than others?
I couldn't answer that because all manufacturers, almost all, if not all, now have some form of frequency lowering. So I think it's hard to draw generalizations.
Yes.
What I found as I've looked at the different settings, different software allows you to have different access and different control over the frequency lowering feature. But it's not, I can't single out one. They all give you fairly good flexibility. And also, most of the manufacturers are already on their second or beyond generation of frequency lowering. So if you've worked with a manufacturer in the past and you only had certain controls and you haven't seen that manufacturer in a while, if you check the software, you may find that they have improved or enhanced your access to frequency lowering controls. For example, Phonak Sound Recover 2 and Widex's Enhanced Audibility Extender, both of those are advanced generations compared to the initial frequency lowering techniques that they were using.
Okay. Thank you, Wendy. It seems like there's no other questions from the audience. So thank you everybody for your participation, and stay on. We will have a new webinar again next week. That will be sinuses. So if you are interested, remember to sign up. I think it's going to be pretty exciting as the one Wendy gave us today. Thank you, Wendy.
Thank you, Wendy.
Thank you, Mariana.
Thank you,
Thank you, Brian. Thanks, everybody.
Bye-bye.
Bye.